1 million miles from Earth, a machine floats in permanent shadow. It carries mirrors coated in gold 48.25 nanometers thick. That is roughly 1,000 times thinner than a human hair. On one side, the sun heats its shield to 80 degrees Celsius. On the other, instruments chill to negative 233 degrees. The difference spans more than 300 degrees across a single spacecraft. This machine catches light that has traveled for over 13 billion years. When it points at patches of sky that appear completely black, it finds something waiting. What if the universe built everything we see far faster than physics allows? The James Webb Space Telescope was supposed to find a quiet cosmos still pouring its foundations. Instead, it found fully formed galaxies the size of our Milky Way, and they existed when the universe was only 3% of its current age. It found supermassive black holes weighing hundreds of millions of suns. They appeared before there was time for them to grow. It found the cosmic web already woven across 13 million light-years. Scientists checked for errors. They corrected for dust, for gravitational lensing, for everything they could imagine. The impossibilities remained. They multiplied. The mathematics of our best models cannot explain what this telescope keeps revealing. Something in the early universe worked differently than we understood. The evidence is arriving now, encoded in ancient light that finally reached us. If you enjoy what comes next, consider subscribing and leaving a like. We begin now. The machine did not arrive at that shadow by accident, and there is a point in space where gravity balances itself. The pull of Earth and the pull of the Sun align in such a way that an object placed there will orbit the Sun in lockstep with our planet. This point is called Lagrange 2. It sits directly behind Earth, hidden from the Sun. A spacecraft stationed there can keep a permanent shield between itself and the three brightest objects in our sky. No sunlight, no Earthlight, no moonlight reflecting off instrument panels. This is where the James Webb Space Telescope waits. Its primary mirror stretches 6.5 meters across. That is wider than a standard two-car garage door. 18 hexagonal segments locked together in a honeycomb pattern, each one shaped from beryllium. Beryllium is light and holds its form at extreme cold. The segments had to survive being folded inside a rocket, launched through the violence of atmospheric escape, and then unfolded in the vacuum of space. Every mirror had to align within a fraction of the width of a human blood cell. The gold that coats each segment serves a specific purpose. Gold reflects infrared light better than almost any other element. Silver might work for visible light. Aluminum might work for certain wavelengths. But for the deep infrared, the light that has traveled the longest through expanding space, gold captures more photons than any alternative. The thickness was not arbitrary. Engineers calculated exactly how much gold was needed to reflect infrared efficiently without adding weight the rocket could not carry. Too little gold and the surface would let infrared slip through. Transparent to the very light the telescope was built to catch. Too much, and every gram would compete with fuel, with instruments, with the folding mechanisms that had to work flawlessly, millions of miles from any repair crew. The coating needed to survive conditions that would destroy most materials. Deep space bathes anything exposed in radiation. Temperature swings crack ordinary coatings. Chemical reactions over years can degrade reflective surfaces. Gold resists all of this. It does not oxidize. It does not corrode. It reflects infrared photons with the same efficiency after a decade as it did on the day it was applied. This machine was designed to catch light that human eyes cannot see. When you look at the night sky, you see stars emitting visible light, blues and whites and reds, and the colors of hot gas burning across the spectrum your retinas evolved to detect. But the most distant objects in the universe do not shine in visible light. Not anymore. A photon that left a distant star billions of years ago began its journey as visible light. Perhaps it was ultraviolet, the high-energy glow of young massive stars. Perhaps it was blue, the color of fusion burning at temperatures our sun will never reach. That photon traveled through space at the speed of light, the fastest anything can move. But space itself was not standing still. The universe has been expanding since its earliest moments. Not expanding into something, but expanding within itself. The distance between objects grows as space stretches. A photon traveling through this stretching medium has its wavelength pulled along with the expansion. And what began as blue light stretches toward red. What began as red stretches toward infrared. What began as infrared stretches toward wavelengths so long that no visible light telescope can detect them. This is called redshift. Redshift is not simply a measure of how far something is. It is a record of time. Each photon that arrives at the Webb telescope carries a timestamp written into its wavelength. The more stretched the light, the longer it has been traveling. The longer it has been traveling, the older the source. A photon with extreme redshift is not showing us something far away. It is showing us something ancient. Consider it this way. Each photon is a time capsule sealed at the moment of its creation. The expansion of space does not destroy the capsule. It stretches it. When the telescope finally catches that photon, and it can read the stretching, like rings in a tree trunk, the wavelength reveals the age. The telescope is not looking at far away. It is looking at long ago. To peer deeper into the universe is to peer backward through time itself. The light arriving now from the nearest star left 4 years ago. The light from the center of our galaxy left 26,000 years ago. The light from the nearest large galaxy left over 2 million years ago. The deeper you look, the further back you see. Webb can see further back than any instrument ever built. When it stares into a patch of sky that appears completely empty to human eyes, it is not searching for nothing. It is waiting. Those patches contain no stars bright enough for our retinas to register. They appear as voids, black gaps between the points of light we recognize. But photons are arriving there. They have been traveling since before the atoms that would become our planet had been forged. The iron in your blood, the calcium in your bones, the oxygen you are breathing right now. These elements were still locked inside stars that had not yet exploded. Those stars were still burning, still fusing lighter elements into heavier ones, still holding themselves together against the crush of their own gravity. And light was already on its way. Photons that left their sources when the universe was young have been crossing the expanding void this entire time. Generation after generation of stars formed, burned, and died while that light was still in transit. Planets condensed from dust. Life emerged on at least one of them. Civilizations rose and fell, and the light kept traveling. And it is arriving now. The telescope catches it. The instruments measure its wavelength. The computers calculate how long it has been stretched by expansion. The timestamp emerges from the mathematics. This is what makes Webb a time machine, not a metaphor, not a poetic flourish. The telescope receives direct physical evidence from eras so distant that nothing from Earth existed yet. The photons are not reconstructions or simulations. They are the actual light emitted by actual objects in the actual past. They crossed the universe to deliver information about conditions that have not existed for billions of years. Webb was sent to look at the early universe. Scientists had specific expectations about what that early universe would contain. Models had been refined for decades. Predictions had been made. Timelines had been calculated. The ancient light was finally arriving, and with it came answers no one was prepared for. Before the light arrived, there was a blueprint. Scientists had spent decades building it. Not a guess, not a rough sketch. A precise mathematical framework describing how the universe should have assembled itself from nothing into everything. The model had a name, lambda CDM, cold dark matter, plus a cosmological constant. It explained how galaxies clustered across the sky. It predicted the faint glow left over from the first moments of existence. It described why space itself was accelerating outward. This was not some dusty theory held together by hope. Lambda, CDM, had been tested against observation after observation. It passed every time. It was the distribution of galaxies across billions of light years matched its predictions. The subtle temperature variations in the cosmic background radiation aligned with its mathematics. The accelerating expansion of space confirmed its inclusion of dark energy. This model worked. It worked for almost the entire history of the cosmos. The blueprint described a universe that assembled slowly, carefully, one step following the next in a mandatory sequence that could not be rushed. Dark matter came first. This invisible substance outweighs the matter you can see and touch by a ratio of 6:1. Dark matter does not interact with light. It passes through ordinary matter like a ghost, but it has mass, and mass creates gravity, and gravity pulls. In the earliest epochs, dark matter was scattered thin across an expanding void. Now, the expansion worked against gravity. Everything was pulling apart. But where the dark matter was slightly denser, gravity had a small advantage. These regions began to contract. Not quickly, not dramatically, just slowly gathering more dark matter into loosely bound regions called halos. This process took hundreds of millions of years. Only after the halos formed could the next step begin. Ordinary matter, the hydrogen and helium forged in the first few minutes of existence, began drifting toward the gravitational wells the dark matter had carved. This gas was hot. It resisted compression. Before it could collapse into anything useful, it had to cool. Cooling takes time. The gas radiated energy slowly, losing heat until it could finally fall inward and gather at the center of these invisible wells. Then, fusion could begin. Hydrogen atoms crashed together under tremendous pressure, releasing energy, creating light. A star was born. But a single generation of stars was not enough. Those first stars burned hot and fast. They contained only the lightest elements. When they exhausted their fuel and collapsed, they exploded as supernovae, scattering newly forged heavier elements into space. Carbon, oxygen, iron, the building blocks of planets and chemistry. This debris mixed with remaining gas. A second generation of stars formed from the enriched material, then a third. It's like a factory assembly line. Picture a production floor with stations arranged in order. Raw materials enter at one end. Each station performs a task that requires the previous station to finish first. You cannot paint the car before the frame is welded. You cannot install the engine before the frame exists. You cannot drive the vehicle off the lot before any of the steps are complete. Each station imposes a delay. Each delay accumulates. The universe was supposed to run this assembly line for hundreds of millions of years before producing anything substantial. Think of stars as furnaces that must burn through entire generations before producing the heavy elements that rocky planets and complex chemistry require. The early universe was supposed to be running those furnaces for the first time, not displaying the finished products. When Webb turned its instruments toward that ancient light, cosmologists knew exactly what they expected to see. Small, dim, fragile. They anticipated finding proto-galaxies. Not real galaxies. The prefix matters. Proto means first, early, primitive. These were supposed to be loose assemblies of stars, barely held together by gravity, still in the process of merging with each other. The universe in those first 500 to 700 million years was supposed to be a construction site. Scaffolding visible, foundations being poured, nothing close to completion. Consider the conditions. Space was still filled with residual heat from the initial expansion. The density of matter was higher than it would be billions of years later, but the structures binding that matter together were just beginning to take shape. The cosmic web, that vast network of filaments connecting galaxy clusters across the void, was not yet woven. It was threads waiting to be spun. Nothing large should have existed. The math was clear. The simulations were definitive. Yet the assembly line had not run long enough to produce a finished product. We thought we knew what the baby pictures would show. We were so confident in our models, so certain about the sequence of events. That confidence, as it turns out, was the thing most worth questioning. Lambda CDM succeeded almost everywhere. It described the universe from a few 100,000 years after the beginning all the way to the present day. It traced the evolution of structure across nearly the entire cosmic timeline. The predictions matched the observations with remarkable precision. But precision is not the same as completeness. The model was calibrated on light from more recent epochs, light that had traveled 5 billion years, 8 billion years, 10 billion years, light from a universe that had already aged into something recognizable. Yet the early chapters were harder to read. The light from those eras had not yet been captured by instruments sensitive enough to detect it. Webb changed that. Webb could see the light that left during the first few 100 million years. Light so stretched by expansion that it had shifted entirely out of the visible spectrum and into the infrared, light that no previous telescope could properly collect. And when that light finally arrived at the instruments, when the detectors registered its wavelength and the computers calculated its age, the timeline did not match. The assembly line had not been followed. The mandatory sequence had been skipped. The construction site was not a construction site at all. Something else was waiting in the ancient light. Something the blueprint never predicted. Something that should not have had time to exist. In February 2023, a study appeared in the journal Nature. The lead author was Ivo Labbe, an astronomer at Swinburne University in Australia. His team had been analysing some of the earliest deep-field observations from the Webb telescope. What they found should not have been possible. 6 objects, 6 candidate galaxies, sitting in a region of time when the universe had barely begun to assemble anything at all. These were not the fragile proto-galaxies everyone expected. These were not the dim, scattered clusters of first-generation stars that the models predicted. These objects were massive, fully formed, already containing as many stars as our own Milky Way. Our galaxy took 13.8 billion years to accumulate its stellar population, yet it had the entire history of the cosmos to gather its mass, merge with smaller galaxies, and build itself into the spiral structure we see today. These 6 objects had done the same work in a fraction of that time. They existed when the universe was between 500 million and 700 million years old. Think about what that means. They had roughly 4% of the time. 4%. And they arrived at the same destination. Erica Nelson of the University of Colorado Boulder helped confirm the observations. So did Joel Ledger of Penn State. Both are experts in measuring the stellar content of distant galaxies. Both double-checked the numbers. The masses were real. The ages were real. The stars were there. The mathematics did not allow them to be there. Yet you cannot build skyscrapers before you have poured the foundations. And the early universe was supposed to be pouring foundations. It was supposed to be mixing concrete and laying rebar. It was supposed to be decades away from anything resembling a finished structure. Webb found skyscrapers already standing. Imagine walking into a construction site on the first day of work and finding a completed 50-story building, not under construction, not half-finished, complete, furnished, and occupied. That is the scale of wrongness these observations represent. The scientific community responded the way scientists usually respond when observations contradict models. They looked for errors. They looked for alternative explanations. They looked for anything that might make the numbers go away. Dust was the first suspect. And as perhaps thick clouds of interstellar material were absorbing and re-emitting light in ways that made these distant objects appear brighter than they actually were. If dust was scattering the measurements, the masses might be overestimated. The galaxies might be smaller than they appeared. Gravitational lensing was the second candidate. Massive objects between us and these distant galaxies could be bending space, magnifying the light like a cosmic lens. Perhaps foreground galaxies were creating illusions. Perhaps what looked like one massive galaxy was actually several smaller ones blurred together by curved space-time. active galactic nuclei offered a third possibility. Perhaps supermassive black holes at the cores of these galaxies were feeding aggressively, pouring out radiation that distorted the measurements. And perhaps the light was coming from the central engines rather than from stars. These were reasonable objections. Any one of them could have explained the anomaly. Scientists hoped at least one of them would make the problem disappear. In November 2025, a study by Katherine Chworowski of the University of Texas at Austin addressed every single objection. Her team mathematically corrected for dust extinction. They accounted for gravitational lensing effects. They modeled the contribution of active galactic nuclei. They stripped away every possible source of contamination and measurement error. The anomaly remained. Not just remained, multiplied. The team confirmed that even after corrections, these objects were still inexplicably massive for their age. The original 6 were not flukes. They were not measurement artifacts. They were not optical illusions created by dust or gravity or feeding black holes. They were exactly what they appeared to be. Impossible. Meanwhile, the pattern was spreading. By August 2025, a study from the University of Missouri had identified 300 additional unusually bright objects in the early universe. 300. Not 6. Not a dozen. 300 points of light that should not have been there, scattered across the deep fields like evidence that refused to stay hidden. Astronomers began calling them universe breakers. Not because they literally broke the universe. The cosmos continued operating exactly as it always had. Stars fused hydrogen, galaxies rotated, light traveled at the speed it always traveled. Nothing physical had changed, and the name referred to what they did to the models, to the equations, to the carefully constructed framework that had successfully described cosmic evolution for decades. These objects pushed lambda, CDM, to its mathematical limits. They stretched the predictions until the predictions snapped. Consider the sequence the model required. Dark matter had to pool first. Ordinary gas had to fall into those pools. That gas had to cool enough to collapse under its own gravity. Stars had to ignite. Those stars had to live and die. Their deaths had to seed the surrounding space with heavier elements. Only then could a second generation of stars form. Only then could rocky planets become possible. Only then could galaxies begin to look like galaxies. Each step takes time, real time, physics time, time that cannot be negotiated or compressed. The universe breakers skipped the sequence. They arrived at the finish line before the race had properly begun. They contained stellar populations that should have required billions of years to accumulate. They displayed chemical compositions that should have required multiple generations of stellar death and rebirth. They exhibited structures that should have demanded slow gravitational settling over cosmic epochs. None of that settling had happened. There had not been enough time for it to happen. The clocks were clear. The distances were measured. The redshifts were calculated. These objects existed in the first few percent of cosmic history. And yet, there they stood, complete, massive, populated with stars that had no right to exist yet. The mathematics did not allow them to be there, but they were there anyway. This was not a small discrepancy. This was not a minor adjustment needed in the margins of the model. This was a fundamental violation of the timeline that cosmology had spent half a century establishing. The rules had been broken. Or perhaps the rules had never been complete. The 6 original candidates were just the beginning. 300 more waited in the data, and the surveys were not finished. Every time the telescope pointed at ancient light, it found more evidence that the early universe did not behave the way the models predicted. The pattern was not shrinking, it was growing. Something happened in the first few 100 million years that the standard model did not anticipate. Yet something accelerated the formation of structure. Something allowed matter to organize itself faster than physics said was possible. The scaffolding was supposed to come first. The foundations were supposed to be poured. The assembly line was supposed to run in order. Instead, The universe delivered finished products before the factory was built. The objects were real. The measurements were confirmed. The errors had been eliminated. What remained was a mystery wrapped in starlight, galaxies that broke the rules, a timeline that did not add up, and a model that suddenly looked less like a map and more like a sketch made by someone who had never visited the territory. The universe breakers had announced themselves. The question now was whether they represented isolated anomalies or something far more troubling. A new physics, a missing ingredient, a chapter of cosmic history that had been written in invisible ink. The telescope continued gathering light. The impossible objects continued multiplying. And somewhere in that ancient glow, the answers waited to be read. The mystery wrapped in starlight demanded an explanation, and explanation required understanding exactly what should have happened, step by step, stage by stage, with no shortcuts allowed. Building a galaxy is not like building a house. A house can be constructed in any order if you have enough workers. Frame the walls before the foundation sets. Install windows before the roof goes on. Cut corners. Improvise. Physics does not care about your schedule, but physics cares deeply about galaxy formation. Every stage depends on the completion of the stage before it. There is no parallel construction. There is only sequence. Think of it like baking bread. You cannot skip the rising time. You cannot make yeast work faster by wanting it to. The chemistry has minimum time requirements, and no amount of pressure changes the physics. The dough rises at the speed. The dough rises. The heat penetrates at the rate heat penetrates. Impatience changes nothing. The early universe should have been a bakery that just opened. Dough still rising. Ovens just warming. Flour barely mixed. Instead, the James Webb Space Telescope found fully baked loaves cooling on the shelf, and the ovens had not been on long enough to bake anything. To understand why this breaks everything, you need to see the recipe. Stage 1 involves gravity doing its slow, invisible work. Before any star can form, and before any galaxy can take shape, matter must first gather. But ordinary matter cannot gather on its own. It is too hot, too scattered, too pressurized by the ambient radiation flooding the young cosmos. Something else has to go first. Something that does not feel that pressure. Something that interacts only through gravity. Dark matter moves through the universe, feeling nothing but the pull of mass. It does not bounce off photons. It does not heat up from radiation. It simply falls toward other concentrations of dark matter, pooling into vast structures called halos. These halos are the invisible wells into which everything else will eventually fall. They are the architecture that ordinary matter cannot see but must obey. This pooling takes time, real time, the kind of time measured in tens of millions of years at absolute minimum. And more realistically, the formation of substantial halos stretches across 100 million years or more. Gravity works at the speed gravity works. It cannot be rushed. It cannot be compressed. The universe was barely 400 million years old when these massive galaxies appeared. The wells had barely begun to form. Stage 2 requires cooling. Once dark matter halos exist, ordinary gas begins to fall inward. Hydrogen and helium tumble toward the gravitational centers. But falling is not enough. The gas heats up as it compresses. Hot gas resists further compression. It wants to expand. It pushes back against the very gravity pulling it inward. For collapse to continue, the gas must radiate away its heat. It must cool. This happens through specific atomic processes. Hydrogen atoms collide, excite, and emit photons that carry energy away into space. The process is efficient enough to work, but it is not fast. Cooling times depend on density, temperature, and the specific atomic physics of the elements involved. These are not variables you can adjust. They are constants written into the fabric of reality. The gas cools at the rate the gas cools. More tens of millions of years pass. Stage 3 brings the first light. When gas cools enough, It begins to collapse under its own weight. Density increases. Pressure builds. Temperature rises again, but this time in concentrated cores rather than diffuse clouds. Eventually, the cores reach temperatures sufficient to fuse hydrogen into helium. Nuclear fire ignites. Stars are born. The first generation of these stars carried a name, Population 3, as if they were made of nothing but hydrogen and helium, pure primordial material untouched by any previous stellar generation. No carbon, no oxygen, no iron, no silicon, just the two lightest elements in existence. These stars burned hot and bright. Many of them were massive, dozens of times the mass of our Sun, perhaps hundreds of times. Their enormous mass meant enormous energy output. Their enormous energy output meant short lives. Even the longest lived among them measured their existence in millions of years, not billions. Stage 4 requires death. Those massive first-generation stars did not fade gently. They exploded. Supernovae ripped them apart, scattering their processed material across surrounding space. Inside their cores, nuclear fusion had built heavier elements: carbon, oxygen, nitrogen, silicon, iron, and the elements that would one day form planets, the elements that would one day form you. But this seeding took time. Each star had to live its entire life. Each star had to exhaust its fuel. Each star had to reach the crisis point where gravity overwhelmed the outward pressure of fusion. Only then came the explosion. Only then did the heavy elements spread, millions of years per stellar lifetime. And you needed many lifetimes, many explosions, many deaths. Stage 5 is rebirth. From the enriched debris of dead stars, a second generation formed. These new stars contained the heavy elements their predecessors had forged. Carbon allowed new cooling pathways. Oxygen enabled new chemistry. The enriched gas could collapse more efficiently than pure hydrogen and helium. Smaller stars became possible. Longer-lived stars became possible. Yet, the foundation for complex solar systems, rocky worlds, and eventually life became possible. But all of this required the previous stages to complete. The second generation could not exist without the first generation dying. The first generation could not exist without gas cooling and collapsing. The gas could not collapse without dark matter wells to fall into. The wells could not form without gravity slowly pulling matter together across cosmic distances. Each stage imposes a timescale. Each scale represents a minimum. Running them in sequence requires adding those minimums together. The total stretches into hundreds of millions of years for even the most optimistic calculations. The problem becomes sharper when you convert the percentages into actual numbers. The universe is 13.8 billion years old, and these impossible galaxies existed when the cosmos was roughly 3% of that age. 3% of 13.8 billion equals approximately 400 million years. That is all the time that had passed. 400 million years for everything. The Milky Way, by comparison, has been accumulating stars for the full 13.8 billion years. Every generation of stellar death and rebirth, every merger with smaller galaxies, every slow gravitational dance across deep time, our galaxy took the full duration of cosmic history to become what it is. These early galaxies achieved comparable results in 400 million years. That is not a small discrepancy. That is a factor of more than 30. 30 times faster than our models permit. 30 times faster than the physics should allow. 30 times faster than the minimum stages could possibly complete. The early universe was not dark or empty. It was luminous, crowded with stars that had no business existing yet. Every calculation said the same thing. The timeline did not work. The stages could not run fast enough. The minimums could not shrink far enough. Something was wrong with the predictions, or something was different about the early universe. The bread was baked. The loaves were cooling. The ovens had been on for barely a moment. And yet, there they sat, complete, massive, impossible. The galaxies themselves were strange enough, structures that should have required cosmic ages of assembly appearing in cosmic childhood, stellar populations that should have demanded multiple generations of death and rebirth somehow already in place, and mass concentrations that should have needed billions of years of gravitational accumulation somehow finished in hundreds of millions. But the galaxies were not the only impossible things lurking in that ancient light. Something else waited at their centers, something even more difficult to explain, something that made the galaxy problem look almost simple by comparison. Sitting at the hearts of many of these early monsters were objects that should not have had time to grow, objects that violated not just the assembly sequence, but the fundamental speed limits of accretion itself, objects whose very existence suggested that the standard picture was missing something essential. The telescope had found the galaxies. The galaxies had raised the questions. The questions were about to get much harder to answer. And the galaxies were impossible, but they were only part of the story. At the heart of many of these early structures, nested deep within their impossible stellar populations, the James Webb Space Telescope found something else, something that made the galaxy problem look almost manageable, something that challenged physics at an even more fundamental level: black holes. Not ordinary black holes, supermassive black holes. To understand why this matters, you need to understand the difference between types of black holes, because the word black hole covers a range of objects so vast that using the same term for all of them borders on misleading. When a massive star dies, when it exhausts its fuel and collapses under its own gravity, it can leave behind a stellar mass black hole, and these objects typically weigh between 5 and 50 times the mass of our Sun. That sounds enormous until you realize what comes next. Gravitational wave observatories like LIGO detect these stellar black holes when they spiral together and merge. The collisions are violent. The ripples in space-time are measurable across cosmic distances. A 50 solar mass black hole is a genuine monster by human standards. But supermassive black holes exist in an entirely different category. Sagittarius A star sits at the center of our Milky Way galaxy. It weighs approximately 4 million times the mass of the Sun, not 4 million times the mass of a stellar black hole, 4 million times the mass of our entire Sun. One star, multiplied 4 million times, compressed into a region smaller than our solar system. That sounds extreme, and it is not even close to the upper limit. The black hole at the center of galaxy M87 was famously imaged in 2019. That silhouette, that glowing ring of superheated matter surrounding absolute darkness, became the first direct visual evidence of an event horizon. The object casting that shadow weighs roughly 6.5 billion times the mass of our Sun. 6.5 billion. Consider the difference between a puddle and an ocean. A puddle might hold a few liters of water. An ocean holds over 1.5 quintillion liters. The gap between them is so vast that comparing them feels almost meaningless. They are not different sizes of the same thing. They are different categories of existence. The difference between a stellar mass black hole and a supermassive black hole is larger than that. And consider it another way. A stellar black hole is a marble. Sagittarius A star is Earth. The black hole in M87 is Jupiter. Same physical process, same fundamental nature, separated by scales so extreme they belong to different conceptual universes. Here is something counterintuitive about these objects. Larger black holes are actually less dense than smaller ones. A stellar mass black hole crushes matter to almost inconceivable concentrations. The density inside one is staggering beyond comprehension. But a supermassive black hole, if you calculated its average density within its event horizon, can be less dense than water. You could theoretically float in it. Not that this would help you. The tidal forces would destroy you long before density became relevant. But the fact remains, supermassive does not mean superdense. It means total mass. All that matter spread across a vast region of warped spacetime. The event horizon of M87's black hole is larger than our entire solar system. Everything inside that boundary adds to the total. The concentration of matter is not what makes it supermassive. The sheer accumulation is. Actually, let me be more precise here. When I say black holes grow, that is not quite the right word. Black holes do not grow like living things. They accumulate mass by capturing matter that falls past their event horizon. Nothing. Not light, not radiation, not information of any kind. Nothing can escape once it crosses that boundary. The black hole simply adds that captured mass to its total. Growing makes it sound gradual and organic. This is more like acquisition, irreversible acquisition. And every particle that crosses the event horizon is gone from the observable universe forever. The black hole claims it. The mass increases. The event horizon expands slightly to accommodate the new total, and the process continues. Over cosmic timescales, this acquisition can be substantial. Gas clouds, asteroids, entire stars, other black holes. Anything that ventures too close becomes part of the total. The supermassive black holes we observe today have been accumulating for billions of years. They sit at the centers of galaxies, fed by the matter that spirals toward them through immense accretion disks. The accretion disk is where the action happens. Matter does not fall directly into a black hole like water down a drain. It spirals inward, accelerating as it goes. The closer matter gets to the event horizon, yet the faster it moves. The faster it moves, the more it collides with other matter. These collisions generate friction. Friction generates heat. The inner regions of an accretion disk can reach temperatures of millions of degrees. This superheated matter glows. It radiates across the electromagnetic spectrum. X-rays, ultraviolet, visible light. The brightest objects in the universe are not stars. They are accretion disks around supermassive black holes in active galaxies. We call these quasars. A single quasar can outshine its entire host galaxy. Hundreds of billions of stars overwhelmed by the light from matter falling into one central object. The black holes at the centers of most large galaxies are not always this active. Sagittarius A star, right now, is relatively quiet. The matter around it is sparse. The accretion rate is low, but in the past, and in other galaxies, these objects can become engines of staggering luminosity. And this brings us to the problem. The James Webb Space Telescope did not just find massive galaxies in the early universe. It found supermassive black holes inside them. Black holes weighing hundreds of millions of times the mass of our Sun. Black holes that existed before the cosmos was even 1 billion years old. Black holes that, by every calculation we can make, should not have had time to accumulate that much mass. The stellar black holes that form when massive stars die start with modest masses. 20 solar masses. 30, perhaps 50 if the star was truly enormous. Starting from that seed, how does a black hole reach hundreds of millions or billions of solar masses? Acquisition. Irreversible acquisition. Matter falling in, crossing the event horizon, adding to the total. But there is a limit to how fast this can happen. A speed ceiling written into the physics of accretion itself. A boundary that governs how quickly any black hole can consume the matter around it. No matter how much fuel surrounds it, no matter how favorable the conditions. That limit has a name. Understanding it requires understanding the forces at war in every accretion disk. The pull of gravity drawing matter inward, and something else pushing back. The supermassive black holes in the early universe existed too soon, too massive, too complete, as if someone had placed fully grown monsters at the centers of galaxies that should not have existed themselves. The telescopes were seeing the impossible compounded. Structures that could not have formed, harboring objects that could not have grown. The mathematics of how black holes acquire mass would reveal exactly how impossible this situation really was. The speed ceiling exists because of light itself. When matter spirals toward a black hole, it does not fall quietly. It screams. Every particle accelerates as it approaches the event horizon. Particles collide with other particles. The collisions generate heat beyond anything found in stellar cores. and heat radiates outward as light. This is the paradox at the heart of black hole growth. The very process of feeding generates energy that opposes further feeding. Light carries momentum. Photons streaming outward from the superheated disk push against incoming gas. The faster material falls inward, the more light it produces. The more light it produces, and the harder it pushes back. Imagine trying to fill a bathtub while someone aims a fire hose at you. You pour water in, and the hose pushes you away. You lean forward and pour faster, and the hose pressure increases. Eventually, you reach a point where you cannot pour any faster. The pushback equals your forward force exactly. You are stuck at maximum capacity, and that capacity is nowhere near what you need. That is the physics of black hole feeding. The limit was calculated by Arthur Eddington in the early 20th century. He was studying how stars hold themselves together. Stars face the same fundamental problem. Gravity pulls inward. Radiation pressure pushes outward. At a certain luminosity, these forces balance perfectly, push harder, and the star tears itself apart. The same mathematics applies to any object trying to grow by consuming matter that produces light. The Eddington limit is not a suggestion. It is not an engineering constraint that clever physics might someday circumvent. It is a speed limit sign on an empty highway, and physics itself is the one enforcing it. There are no exceptions. There are no shortcuts. Every black hole in the universe is bound by this law. At the Eddington limit, if feeding at the absolute maximum sustainable rate, a black hole approximately doubles its mass every few tens of millions of years. Start with a seed weighing 30 times the mass of our Sun. Give it 70 million years at maximum feeding rate. It becomes 60 solar masses. Give it another 70 million years, 120 solar masses. The doubling continues, but exponential growth from such a small starting point requires many doublings to reach truly enormous scales. To grow from 30 solar masses to 300 million solar masses requires roughly 23 doublings. 23 doublings at 70 million years each. Run the arithmetic. The answer exceeds 1.5 billion years. That is the time a black hole needs to grow from stellar seed to supermassive giant. Not the time it should need, at the time it cannot possibly beat. The Eddington limit is the theoretical ceiling for continuous, uninterrupted, maximum efficiency feeding. It is the best-case scenario written into the laws of physics. Here is what makes the problem worse. Real black holes do not feed continuously. Real accretion is chaotic. Gas does not flow smoothly toward an event horizon like water through a pipe. It arrives in clumps. It forms unstable structures that fragment and reform. Powerful jets erupt from the black hole's poles, blasting material away before it can cross the event horizon. Nearby star formation heats the surrounding gas, disrupting the feeding process. A black hole might spend millions of years at peak feeding rate, then billions of years barely consuming anything at all. The fuel runs out. The accretion disk empties. The black hole goes quiet, waiting for the next meal to wander close enough to capture. Studies of nearby supermassive black holes reveal feeding rates far below the Eddington limit. Most of the time, these objects consume material at 1% or less of their theoretical maximum. Some are essentially dormant, surrounded by sparse halos of gas that barely provide any sustenance at all. The Eddington limit assumes perfect conditions maintained forever. Reality provides intermittent meals separated by vast stretches of starvation. This transforms the timeline problem from concerning to catastrophic. The 1.5 billion year minimum assumed that a black hole never stopped feeding, never experienced a disruption, never ran out of material, never had its meal blown away by its own radiation. It assumed the most generous possible interpretation of black hole growth physics. Real growth rates suggest the journey from stellar seed to supermassive giant should take 3 billion years, perhaps 5 billion, perhaps longer. depending on the environment and the availability of fuel. The Milky Way's central black hole has been accumulating mass for nearly the entire history of the universe. It has had access to the gas at the center of a major galaxy for over 13 billion years. In all that time, it has reached 4 million solar masses, massive by any human standard, a speck compared to the monsters lurking in quasars. The black holes in distant active galaxies, the ones powering the brightest beacons in the cosmos, weigh billions of solar masses. They took billions of years to reach those scales, and the mathematics works out. The timeline makes sense. Then, the James Webb Space Telescope pointed at the earliest universe and found black holes weighing hundreds of millions of solar masses. Objects that existed before the cosmos reached its 500th millionth birthday. Objects that should not have had time to accumulate even a fraction of their observed mass. The mathematics simply does not work. Start with a 30 solar mass seed. Feed it continuously at the Eddington limit. Never allow a single interruption. Never let the fuel supply dip. Maintain perfect conditions for every moment of every million years. The black hole still cannot reach hundreds of millions of solar masses in 500 million years. The physics forbids it. And 500 million years is the generous interpretation. And some of these objects were found at even earlier epochs. Some existed when the universe was barely old enough to have formed stars at all. The seeds themselves should not have existed yet. The matter that would become the seeds was still diffuse gas spread across cooling space. A recent study from Madrid identified light sources at redshifts indicating an age of 100 to 200 million years after the Big Bang. Objects at those distances, if they contain the supermassive black holes their spectra suggest, existed before most models allow for the formation of any black holes at all. The speed limit is clear. The distance is measured. The time available is known. These three facts contradict each other absolutely. Something in our understanding must be incomplete. Either the speed limit is wrong, or the starting point is wrong, or our measurement of time itself contains errors we have not identified. The Eddington limit has been tested and verified across countless observations. It applies to stars. It applies to neutron stars. It applies to black holes of every size we can measure directly. The physics is not speculative. It emerges from fundamental principles that govern how light interacts with matter. If the speed limit holds, then something else gave these early black holes a head start. Something created seeds far more massive than dying stars could produce. Something allowed black holes to begin their growth from a position that would require far fewer doublings to reach the observed masses. The question shifts. The mystery deepens. If stellar black holes cannot explain the monsters in the early universe, but what formed them? What process bypassed the slow crawl of stellar evolution and created objects massive enough to reach supermassive scales in less than 500 million years? The answer, if one exists, requires physics that was not in the textbooks before the James Webb Space Telescope began sending data home. The calculation begins with a single number, 800 million years. That is the absolute minimum time required for a black hole seed to reach 1 billion solar masses. 800 million years of continuous feeding, not sporadic, not interrupted, continuous. Every moment of every era, matter falling inward at the maximum rate physics allows. No pauses, no disruptions, no dry spells when the fuel runs out. 800 million years. Yes, the universe was less than 500 million years old when the James Webb Space Telescope found supermassive black holes already in place, already massive, already defying the arithmetic that should govern their existence. The math teacher walked into class and found the answer on the board before the question had been asked. The runner crossed the finish line before the starting gun fired. Let that image settle for a moment. Imagine attending a birthday party for a child turning 5 years old. The decorations hang from the ceiling. The candles stand on the cake, 5 of them. And sitting at the table is a person who appears to be 90 years old. Not a grandparent visiting, not a guest from another generation. This person was born at this party 5 years ago. You check their birth certificate. You examine their bones. Yet you measure the wear on their cells. Every test confirms the same impossible answer. They are 90. They were born 5 years ago. The mathematics of human aging does not permit this. A person cannot accumulate 90 years of biological wear in 5 years of existence. The rate of aging has limits. The body changes at speeds that cannot be bypassed. You cannot age 90 years in 5. The contradiction is absolute. This is precisely what Webb found in the early cosmos. Black holes that had accumulated more mass than time allowed. Objects that had grown further than the speed governor should permit. The Eddington limit acts as a regulator bolted onto every black hole engine in existence. It sets the maximum rate at which a black hole can consume material, feed faster, and the radiation generated by the infalling matter pushes everything else away. The gas that would become food gets blown back into space. The black hole chokes on its own brightness. Webb found engines that had somehow traveled further than the speed limit should allow, in less time than the journey should take. The early universe was not quiet and slowly assembling. It was violent, churning with black holes that had no right to exist. The 800 million year figure sounds generous. It is. The calculation assumes perfect conditions from the first heartbeat of time. It assumes the black hole seed appeared immediately after the cosmos began. It assumes that seed began feeding at the maximum rate without a single pause. Every second of every million years, a matter streaming into the event horizon at precisely the Eddington rate. But reality does not cooperate with theoretical ideals. The first stars needed time to form. Primordial hydrogen had to cool. Gas clouds had to collapse under their own weight. The nuclear furnaces had to ignite, burn through their fuel, and die. Only then could stellar remnants leave behind black hole seeds. This process consumed the opening chapter of cosmic history. The first few 100 million years were spent simply creating the conditions for black holes to be born at all. No seeds existed during this era. No growth could begin. When you account for this delay, the timeline shifts from improbable to absurd. The 800 million year minimum assumes the clock starts immediately. But the clock could not start until seeds existed. And seeds required stars. And stars required conditions that did not stabilize until well after the Big Bang. The study led by Pablo Pérez González at the Center for Astrobiology in Madrid examined light sources at extreme distances. Redshifts of 17 and 25. Numbers that correspond to a cosmos barely emerging from its infancy, 100 to 200 million years after everything began. At those epochs, the universe should have contained only cooling gas and the earliest generation of stars just beginning to burn. Instead, the signatures suggest massive black holes already present, already anchored in place, already influencing their surroundings with gravitational authority. Consider what this means. 100 million years is roughly 10% of the minimum growth time, and it is the equivalent of running 1/10 of a marathon and claiming you finished the race. The mathematics does not bend. The physics does not negotiate. Something else happened. Something our models do not explain. Picture yourself planning a cross-country journey. Your car can travel at a maximum speed. You know the distance. You calculate the minimum time required to arrive. 8 hours perhaps. You cannot arrive in 4 unless you find a way to exceed the maximum speed your engine allows. The laws governing your engine do not care about your schedule. They enforce themselves regardless of your plans. Now imagine arriving at your destination before the journey began, not faster than expected. Before. This is what the timeline paradox represents. The black holes existed before the minimum required growth time had elapsed, and before the seeds themselves should have formed. The Eddington limit is not a suggestion. It emerges from the fundamental relationship between gravity and radiation. Light carries momentum. Photons push against the particles they strike. When a black hole feeds, the matter spiraling inward heats to extreme temperatures. That heat radiates outward. That radiation pushes against the incoming flow. Too much feeding generates too much radiation, which blocks further feeding. The system self-regulates. The growth caps itself. This limit has been verified across countless observations. It applies at every scale we can measure directly. It operates in stellar environments. It governs neutron star behavior. It shapes the physics of active galactic nuclei across the observable cosmos. The mechanism is not theoretical speculation. It is observed reality. And yet, the early universe contained black holes that appear to have bypassed it somehow. The contradiction cannot be resolved by adjusting assumptions about feeding rates. Even perfect conditions at the theoretical maximum produce timelines longer than the available window. The problem is not that our assumptions are too pessimistic. The problem is that even our most optimistic assumptions fail to account for what Webb observed. Something granted these black holes a head start. Something created seeds far more massive than dying stars produce. Something allowed growth to begin from a foundation that required fewer steps to reach the observed result. The question is no longer whether the standard picture is complete. The observations have answered that. The question becomes sharper now. But what process operated in the young universe that could generate massive seeds directly? What pathway existed that we did not predict? The cosmos wrote an answer to a question we had not yet learned to ask. The black holes are the answer. We are still searching for the question. The standard picture failed, that much is clear. The seeds were too small. The time was too short. The growth limits too strict. The black holes exist anyway. So physicists began searching for pathways that should not exist. Alternative routes, hidden doors, ways to build massive objects without walking through the slow corridors that stellar evolution requires. The first proposal is the most radical: direct collapse. Picture a cloud of primordial gas drifting through the early universe. This cloud weighs 100,000 times the mass of our Sun, and in the modern universe, such a cloud would fragment. It would break into smaller pieces. Each piece would condense into a star. Stars would live and die. Some would leave black holes behind. The process would take hundreds of millions of years. But the early universe was different. Under very specific conditions, a cloud this massive might not fragment at all. It might simply fall inward, collapse entirely, skip the stellar phase and become a black hole directly. No star formation, no fusion, no generations of burning and dying, just gas becoming a gravitational pit in a single catastrophic event. Direct collapse is like skipping childhood entirely and being born as an adult. No infancy, no growth phase, just sudden existence at full size. A seed that begins at 100,000 solar masses does not need 20 doublings to reach the scale Webb observed. It arrives already large, already capable of growing into something truly massive within the available window. The physics that would allow this are precise. The gas must remain warm enough to avoid fragmenting. It must be shielded from the cooling effects of heavy elements. It must exist in a pocket of the universe where conditions conspire against star formation. Such conditions may have existed only in the first few 100 million years. A narrow window, then closed forever. The second pathway involves the first generation of stars themselves. Population 3 stars. These were the original furnaces, born from clouds of pure hydrogen and helium with no heavier elements, no carbon, no oxygen, no metals of any kind. This matters because heavier elements act as cooling agents. They allow gas to radiate heat efficiently. When gas can cool, it fragments into smaller clumps. Smaller clumps form smaller stars. Our Sun exists because the gas that formed it could cool efficiently. Population 3 stars formed before any of those cooling agents existed. The gas remained hotter. The clumps remained larger. The resulting stars may have grown to hundreds or even thousands of times the mass of our Sun. When such a star exhausted its fuel and collapsed, it would leave behind a black hole seed proportionally massive. Not 20 solar masses, perhaps 1,000, perhaps more. These stars would have burned hot and bright and brief. Their lives measured in millions of years, not billions. And when they died, they seeded the universe with black holes far larger than anything the standard stellar pathway produces. The third pathway relies on mathematics of a different kind, rapid merging. In the modern universe, black holes are sparse. The distances between them are measured in light years. Collisions happen, but rarely. Two black holes might orbit each other for millions of years before spiraling together. The early universe was not like this. Everything was closer together. The cosmos had not yet expanded to its current dilute state. Black holes forming in the same proto-galaxy would have found each other quickly. They would have merged. The resulting black hole would be larger. It would find another partner, merge again, a cascading process, each merger building towards something more massive. In dense early environments, as this runaway growth could have produced black holes far exceeding what any single stellar collapse allows. The universe itself was smaller. The hunting grounds were richer. The prey was plentiful. And then there is the strangest pathway of all. In September 2025, astronomers found a population of objects they called little red dots. These are not ordinary galaxies. They are not ordinary black holes. They may be something that existed only in theory until the telescope forced us to consider them seriously. Black hole stars. The concept sounds like a contradiction. A star is a ball of fusing plasma held together by gravity. A black hole is a gravitational pit from which nothing escapes. How could these two things coexist? Imagine a massive black hole sitting at the center of a bloated envelope of gas. The black hole feeds on the inner layers. The radiation from that feeding pushes outward. The outer envelope remains inflated, puffed up, supported against collapse by the very process that should be consuming it. Black hole stars, if they exist, are something like a parasite and host merged into a single organism, neither fully alive nor fully dead, feeding on itself in a way that should not be stable, but apparently is. A configuration that appears nowhere in the modern universe. A creature of the early cosmos alone. This is the part that gets me. We are not just saying our models are incomplete. We are saying the universe may have had entirely different modes of operation in its infancy, ways of building things that it then lost forever. It's like a construction technique from antiquity that we can see the results of, but will never be able to replicate. The pyramids of the cosmos, built by methods we can only guess at. None of these explanations has been confirmed. That is worth sitting with for a moment. Direct collapse has never been observed. Population 3 stars have never been directly detected. Their existence is inferred from their absence, from the fingerprints they left behind, from the chemistry of galaxies that formed after they died. Black hole stars remain theoretical. The little red dots are candidates, possible examples, but the confirmation that they represent this exotic configuration has not arrived. And yet, none of these pathways can be ruled out either. Each one requires physics we have not directly witnessed, conditions that may have existed only in that first narrow window of cosmic history. A window that opened when the universe ignited its first light and closed when the expansion cooled everything beyond the threshold these processes require. We are proposing explanations for a phenomenon using mechanisms we have never seen and may never be able to recreate. The early universe may have operated by rules that no longer apply anywhere in the observable cosmos. The laboratory conditions are gone. The experiment cannot be repeated. Yet we have only the results. 4 pathways, 4 possible answers, each one stranger than conventional physics allows, each one necessary because the conventional physics cannot explain what hangs in the observational data. The black holes are too massive. The time was too short. Something bridged that gap. Something operated in the young cosmos that we can only theorize about now. The mechanisms may be forever beyond direct confirmation, but their products remain. visible, measurable, demanding explanation. The impossible galaxies and impossible black holes were troubling enough on their own. Individual anomalies might be explained away, statistical outliers dismissed as measurement errors. But the James Webb Space Telescope found something more unsettling than individual objects defying expectation. And it found that these objects were not scattered randomly through the early cosmos. They were organized, connected, arranged into structures that should have taken far longer to weave. The galaxies and black holes were not the only things that arrived ahead of schedule. The cosmic web, it is not a metaphor. It is not a convenient phrase scientists use to describe something complex. It is the actual architecture of everything, the physical structure of the universe at the largest scales imaginable, the scaffolding upon which all of existence hangs. If you could somehow step outside our galaxy and keep traveling outward, past the neighboring galaxies, past the local group, past everything familiar, and then somehow zoom out until you could see billions of light years all at once, you would see it. A vast three-dimensional network of filaments stretching across the void, threads of matter connecting clusters and superclusters, a web woven through the darkness itself. The comparison to a spider's web is almost too simple. A spider builds in 2 dimensions. This structure exists in 3. Picture strands of silk extending not just outward, but upward and downward, and in every direction simultaneously. Where the strands cross, where multiple filaments intersect, you find dense knots of matter. Galaxies cluster at these intersections, like dewdrops caught where threads meet. The spaces between the filaments are not merely empty, they are actively drained. Voids stretching tens of millions of light years across. Regions where almost nothing exists. The matter that might have been there has been pulled away over cosmic time, or drawn toward the filaments, channeled along invisible highways toward the crowded intersections. Think of dark matter as invisible scaffolding that ordinary matter clings to. You cannot see the scaffolding itself, but you can see everything that hangs from it. Every galaxy, every cluster, every supercluster. They trace out the underlying structure like ornaments hanging from an invisible tree. This is worth sitting with. The galaxies we observe are not scattered randomly across the sky. They are arranged along these filaments with mathematical precision, their positions dictated by structures that formed in the first fractions of a second after the Big Bang, before the first stars, before light itself could travel freely through the cosmos. The seeds of this web were planted in the quantum fluctuations of the infant universe. Now, those tiny fluctuations were almost nothing. Slight variations in density, regions where matter was ever so slightly more concentrated than the space around them. But gravity is patient. Gravity never forgets. Over time, those slightly denser regions pulled in more matter, which made them denser still, which pulled in more matter. A feedback loop that ran for billions of years. The denser regions became the filaments. The emptier regions became the voids. And at every intersection, where multiple filaments met, matter accumulated into the densest structures in the universe. Galaxy clusters containing thousands of galaxies. Superclusters containing multiple clusters. All connected by these threads of dark matter and gas stretching across the void. Matter does not float randomly through the universe, as it follows these invisible highways, channeled by dark matter into predetermined paths. Gas flows along the filaments like water through river channels, feeding the galaxies at the intersections, draining the voids of anything that might have remained. If you watch this process unfold at cosmic speeds, you would see something like breathing. Matter inhaled by the filaments, exhaled into the voids. A slow cosmic respiration spanning billions of years, the universe organizing itself into larger and larger structures through nothing but gravity and time. The standard model had a clear prediction for how long this should take. Gravity works slowly. It does not build instantly. The earliest fluctuations were tiny, nearly imperceptible variations in an otherwise smooth cosmos. Pulling that matter together required time. in enormous amounts of time. The models predicted that significant filamentary structure would not appear until the universe was several billion years old. The first few 100 million years should have been chaos, hot gas cooling, small clumps forming, proto-galaxies beginning to coalesce, but the grand architecture, the web itself, that should have come later, much later. The universe needed time to organize itself at these scales. Scientists measure this structure by looking at groups of galaxies at different distances. Remember that distance in space is also distance in time. Light from a galaxy 30 million light-years away shows us that galaxy as it was 30 million years ago. Light from a galaxy 3 billion light-years away shows us that galaxy as it was 3 billion years ago. By comparing galaxies at different distances, astronomers can watch structure formation unfold. Like comparing photographs of a child at different ages, you can see how the web assembled itself, how the filaments strengthened, how the voids emptied, how the clusters grew. Closer galaxies show us the recent universe. Distant galaxies show us the ancient universe. By mapping enough of them, scientists can construct something like a time-lapse photograph of the cosmos. Snapshots spanning billions of years compressed into a single dataset. This is how we know the cosmic web exists. We can map it. We can measure the filaments. We can chart the voids. We can identify the clusters where multiple filaments meet. The structure is real, measurable, precise, and it was supposed to take an enormous amount of time to weave. Oh, the mathematics seemed clear. Start with nearly uniform conditions. Apply gravity. Wait. The fluctuations grow slowly at first, then faster as they accumulate more mass. Eventually, after billions of years, the web emerges. Filaments stretching across the void, voids emptying between them, clusters forming at the intersections. This timeline seemed settled. The cosmic microwave background, that ancient light from when the universe first became transparent, showed us the initial conditions. The fluctuations were there, tiny variations in temperature corresponding to tiny variations in density. The seeds were planted. We knew how strong they were. We could calculate how long they would take to grow. The answer was billions of years, not hundreds of millions, billions. And the web should have assembled itself gradually over cosmic time. The earliest glimpses of significant structure should appear perhaps 2 or 3 billion years after the beginning. The full architecture should emerge later still. The models were consistent. The mathematics was sound. The initial conditions were measured. The growth rate was calculated. Everything pointed toward a slow and patient construction project. Gravity weaving its web strand by strand over billions of years. And then the James Webb Space Telescope looked back to the earliest epochs. It looked at light that had traveled for billions of years. Light from the young universe. Light from the era when only chaos should have existed. Before the web should have been woven. Before the filaments should have formed. And before the great architecture should have assembled itself. The individual anomalies had been troubling enough. Galaxies too massive for their age. Black holes too large for the time they had to grow. Each one a point of impossibility in the observational data. But points can be dismissed. Individual outliers might be measurement errors. Statistical flukes in the vast dataset. Unusual but explicable deviations from the expected pattern. What made dismissal impossible was the discovery that these objects were not scattered randomly through the early cosmos. They were connected, arranged along structures, organized into patterns that looked suspiciously like the cosmic web itself. The galaxies and black holes were not the only things that arrived ahead of schedule. The architecture they inhabited was also too developed, too organized, too mature for the age of the universe when it existed. The web was supposed to take time. It was supposed to emerge gradually from chaos. But the James Webb Space Telescope found something that looked like a web already in place, already organized, already channeling matter along predetermined paths. The individual impossibilities had combined into something larger, a structural impossibility, an architectural impossibility. The very framework of the cosmos assembled before it should have been possible to assemble it. The framework was already there. The skeleton of the cosmos, assembled and operating in an era when only scattered fragments should have drifted through the void. And within that framework, yet the James Webb Space Telescope found something that forced astronomers to reconsider everything they thought they understood about how structure emerges. They called it the cosmic vine, a chain of more than 20 galaxies, not scattered randomly, not drifting in isolation, connected, linked together across a span of over 13 million light-years, a structure so vast that light itself would need 13 million years just to cross from one end to the other. And it was already woven and functioning when the universe was only a few billion years old. Consider what that means. The galaxies in this chain were not waiting to find each other. They were not slowly drifting toward eventual connection. They were already organized, already participating in a shared gravitational dance, already behaving like members of a community that should have taken much longer to form. But the cosmic vine held an even stranger secret, something that transformed an architectural anomaly into a temporal impossibility. Several of the galaxies within this chain had already quenched. In astronomy, quenching is a specific term. It describes what happens when a galaxy exhausts its supply of gas. Without gas, no new stars can form. The stellar nurseries fall silent. The furnaces go cold. A quenched galaxy is a retired galaxy, one that has finished the work of creation and entered a long twilight. Think of it this way. A quenched galaxy is like a worker who has already lived an entire career, born into the cosmic workforce, spent billions of years creating stars, building structure, burning through its reserves of raw material, and finally, exhausted, retiring from active duty. That process takes time, an enormous amount of time. Yet here they were, retired workers, in a universe that was supposed to still be in its first day of existence. The mathematics did not allow them to be there, not as an accounting error, not as a rounding problem in a distant calculation. This was something more fundamental. The models that described how galaxies form, how they consume their gas, how they eventually quench. Those models required timescales that simply were not available. The universe was too young. The clock had not run long enough. And yet, there they were, quenched, finished, resting at the end of lives that should have been impossible to live. The universe did not wait. That phrase will become important. It has because what the James Webb Space Telescope revealed was not a single anomaly, not a handful of outliers that could be dismissed or explained away. It was a pattern, a consistent refusal by the early cosmos to respect the timelines we had calculated for it. Researchers catalogued over 1,600 galaxy groups and proto-clusters. These structures spanned an enormous range. Some existed 12 billion years ago. Others dated back to just a few billion years after everything began. The entire early universe was more organized, more mature, more architecturally sophisticated than any model had predicted. A 2025 study from Cambridge examined 250 young galaxies. These were galaxies that existed only 800 million years after the beginning, still in what should have been the cosmic dawn, at the infancy of structure formation. What the researchers found was not infancy, it was violence, intense internal turbulence, chaos churning within galaxies that should have been too primitive to exhibit such complexity, gas swirling at tremendous speeds, stars forming in bursts of activity that defied the gentle, gradual assembly our theories described. The early universe was not quiet. It was not orderly. It was a maelstrom of activity that should have prevented organized structure from emerging. And yet, organized structure emerged anyway. Early in 2025, astronomers made another discovery that seemed almost designed to contradict itself. They found a galaxy they called the Big Wheel, a massive spiral galaxy, elegant arms sweeping outward in graceful curves, ordered structure. peaceful rotation, and the kind of galaxy that should only exist after billions of years of calm, gradual evolution. The Big Wheel existed in the first 2 billion years of cosmic history. Picture finding a completed cathedral standing peacefully in the middle of an active war zone. The chaos that should have destroyed it simply had not. The violence that should have torn its structure apart had somehow left it untouched. The Big Wheel rotated in serene dignity through an era defined by cosmic collisions and gravitational mayhem. How do you explain that? The early universe was a place of constant mergers, galaxies smashing into each other, smaller structures being torn apart and absorbed by larger ones. The gravitational environment was hostile to the delicate organization that spiral arms require. Yet there it was, spinning, beautiful, impossible. A Lamia Mola of Swinburne University offered a suggestion that cuts even deeper than the observations themselves. Perhaps these structures hint at pathways for galaxy growth that simply do not exist in the modern universe. Let that thought settle. Not just faster growth, actually different growth. Ways of building cosmic structure that worked in the first billion years and then became impossible as the universe aged. Processes that operated under conditions we can no longer recreate or observe directly. Rules that applied once and then stopped applying. We are not just seeing things that arrived ahead of schedule. We may be seeing the results of processes that no longer operate anywhere in the observable cosmos. Like finding evidence of a construction technique that has been lost for billions of years. A method that built the foundations of everything we see and then vanished from the universe completely. The standard models describe how things work now, how galaxies form in the modern cosmos, how black holes grow under current conditions, how structure assembles given the physics we can observe and test. But the early universe may have played by different rules entirely. The mathematics did not allow these structures to be there. Not the mathematics of our models, not the equations we derived from observations of the nearby universe. We calculated growth rates, we measured gas consumption, we tracked how long it takes for galaxies to exhaust their star-forming material and finally quench. All of those calculations produced timelines that the early universe ignored. Now, the universe did not wait for our equations to permit its existence. It did not pause while physicists refined their models. It simply built, organized, matured, quenched, and left us to discover the evidence billions of years later, staring at structures that should not be there, trying to understand rules that may no longer apply. This is not a problem with individual objects anymore, not a handful of oversized galaxies or unexpectedly massive black holes. This is systemic. The entire architecture of the early cosmos was more developed, more sophisticated, more complete than anything our theories predicted. We built our understanding of cosmic evolution from the universe we could see, the nearby galaxies, the familiar structures, the processes operating in the current epoch. And we assumed those processes had always operated the same way, that the rules were universal, that physics in the first billion years worked the same as physics today. The James Webb Space Telescope is showing us that assumption may have been wrong. Not slightly wrong, fundamentally wrong. The early universe may have been a different kind of place entirely, a place where matter organized itself through pathways we have never witnessed, where galaxies grew and aged and retired through mechanisms that left no trace in the modern cosmos. The cosmic vine, the quenched galaxies within it, the 1600 protoclusters scattered through the early universe, the big wheel spinning in defiance of chaos, each one a piece of evidence pointing toward the same conclusion. Something happened in the first billion years that our models cannot explain. Something that built the framework of reality faster than physics should allow. Something that left us with a cosmos that was already mature before it should have finished being born. And that something may be gone forever, vanished into the expanding darkness, operating only once, in conditions we can never recreate, through processes we may never fully understand. But here is something important. something that can get lost in the accumulation of anomalies and impossible timelines. The standard model of cosmology is not broken. That distinction matters. Lambda CDM, the model that describes how the universe evolved from its earliest moments to today. It remains the most successful framework ever constructed for understanding the cosmos. And this is not a model that has been guessing. This is not a framework that has been stumbling in the dark. It has made predictions. Specific, testable, precise predictions. And those predictions have been confirmed again and again. The cosmic microwave background radiation. That faint glow left over from when the universe was young enough for light to travel freely for the first time. The model predicted the exact pattern of that radiation, the tiny temperature variations, the specific frequencies, the way those ripples would be distributed across the entire sky. When satellites mapped that glow in extraordinary detail, the measurements matched the predictions with stunning accuracy. The large-scale distribution of galaxies in the modern universe, where matter should clump, where voids should form, how clusters should arrange themselves across hundreds of millions of light years. The model predicted that distribution, and when surveys catalogued millions of galaxies across vast stretches of space, the patterns matched. The accelerating expansion of the cosmos, dark energy pushing everything apart faster and faster. The model suggested this acceleration before astronomers measured it directly. It predicted what we would find, and when the data came in, the prediction held. This is a model that works. A model that has earned its place at the center of cosmology through decades of successful predictions. The mathematics describes reality. The equations match what we observe in the universe around us. So the James Webb Space Telescope has not proven that model false. It has proven that model incomplete. Those are different things, profoundly different things. Consider a map of a continent you have never fully explored. The cartographers did their work carefully. They traced the coastline with precision. They marked the major rivers where they found them. They sketched the mountain ranges that rose above the horizon. They noted the cities and the roads connecting them. Every place they visited, they recorded accurately. Every region they surveyed, they documented faithfully. You travel through the mapped territories yourself. You check the coastline against the drawing. It matches. You follow the rivers on the page. They flow where the map says they flow. You climb toward the mountains. They rise where they should rise. And the map works. The map is accurate. The map describes reality as you experience it. Then one day, an expedition reaches a corner of the continent no cartographer ever visited, a remote region beyond the surveyed territories. And the explorers find something unexpected, a forest that is not on the map, rivers flowing in directions the cartographers never recorded, mountain passes cutting through ranges that the original surveys never reached. The expedition returns with news of these unmapped features, and the question becomes, what do you do with that information? The map is not wrong about the places it already described. The coastline is still accurate. The rivers still flow where they were marked. The mountains still rise where they were sketched. Everything the cartographers recorded remains true. They simply missed features in a region they never explored. The map is incomplete. Not incorrect, incomplete. Webb is that expedition. The telescope has reached the unmapped territory, the earliest ages of the cosmos, the first billion years that previous instruments could not see clearly, and the territory does not look like the cartographers predicted. That does not mean the cartographers failed. It means they had limited information. They mapped what they could see. They described what they could reach. And they did that work brilliantly. The problem was not their skill. The problem was the boundary of their exploration. We mapped the cosmos from the universe we could observe, the nearby galaxies, the structures within reach of our previous instruments, the processes operating in the epoch we inhabit. But we assumed the rules we discovered here would apply everywhere, would apply everywhen. We extrapolated backward through time using physics we measured in the present. That extrapolation works remarkably well for most of cosmic history. The model describes the universe we can see with extraordinary precision. It predicted features we had not yet measured. It guided our understanding of processes we had not yet witnessed. The mathematics is elegant. The framework is powerful. The predictions are verified, but the earliest ages were beyond our reach. The first billion years existed only in theory, in simulations, in equations that projected backward from what we knew. We could not see that era clearly. The light was too faint, too stretched, too ancient for our instruments to resolve. Webb changed that. A Webb reached the unmapped corner, and Webb found features that the extrapolation did not predict. Galaxies that should not be there, black holes that should not exist, structures that should not have formed, an architecture that should not have been in place. The model is not wrong about what it describes. It is missing information about an era it could never directly observe. We wrote equations for conditions we had never seen. We made assumptions about processes we had never witnessed. And some of those assumptions appear to need revision. This is how science works. Not through collapse, not through the destruction of everything that came before, through expansion, through the incorporation of new data, through the refinement of frameworks that were always understood to be provisional. Every model in science is a work in progress. Every equation is an approximation waiting to be improved. Every theory is a description of reality that will eventually be superseded by a more complete description. This is not failure. This is the process. There is something else Webb has revealed. Something about the sheer density of existence hiding in apparent emptiness. The telescope pointed at a patch of sky, a tiny patch, roughly the size of 3 full moons held at arm's length. Look up at the night sky and find a spot that appears dark, empty, a gap between the visible stars. That is the kind of region Webb studied. It watched that patch for hundreds of hours, collecting every photon that arrived, building an image from the faintest light in the cosmos. And when the image resolved, it contained nearly 800,000 distinct galaxies. 800,000. In a patch of sky you could cover with your thumb. Not stars, galaxies, each one containing billions of stars, each one hosting its own planetary systems, its own cosmic history, its own story of formation and evolution stretching back billions of years. To print that single image at the resolution of its finest details would require a surface 4 meters tall by 4 meters wide, a wall of galaxies, each point of light a universe unto itself, each tiny smudge a collection of worlds beyond counting. The sky is not empty. The darkness between visible stars is not void. It is crowded beyond comprehension. We simply lacked the instruments to see the crowds until now. The universe has been there all along, patient, dense, filled with structures and histories we are only beginning to glimpse. Webb did not break our understanding of the cosmos. It expanded the territory we can explore. It pushed the boundary of the known into regions we had only imagined. And yes, what it found there does not match what we expected to find. The territory does not look like the map predicted, but that is not a crisis. That is a beginning. The cartographers did their work well. Now we have new regions to chart, new features to understand, new questions to answer about an era we are finally able to see. The model will grow to accommodate what Webb has found. The equations will be refined. The simulations will be adjusted. The understanding will deepen. This is not the end of cosmology. This is cosmology doing exactly what cosmology is supposed to do, reaching further, seeing more, learning that reality is stranger and more wonderful than our previous instruments allowed us to imagine. The universe has no edge, no wall, no physical barrier marking where existence ends and something else begins. There is no sign posted at the frontier of reality telling travelers they have reached the limit. And yet, there is a boundary, a real one, a boundary that defines everything we can ever know. It is not made of matter. It is not made of energy. It is made of something stranger. It is made of information, or rather, the absence of it, Picture yourself standing on a shore. The ocean stretches to the horizon in every direction. That line where water meets sky is not a wall. Nothing physical exists there. If you sailed toward it, you would never reach it, and it would recede as you approached. And yet, it defines the limit of what you can see from where you stand. The universe has a horizon like that, a boundary beyond which no light, no signal, no information of any kind can ever reach us. Not because something is blocking it, because there simply has not been enough time. The observable universe extends approximately 46 billion light years in every direction from Earth. Let that number settle for a moment. 46 billion light years, that is the radius of everything we can ever hope to detect. Everything beyond that sphere is invisible to us. Not dark, not hidden, just permanently unreachable. Here is where it gets strange. The universe itself is only 13.8 billion years old. Light travels at a fixed speed. If the universe has only existed for 13.8 billion years, how can we see objects 46 billion light years away? The light would not have had time to reach us. The answer reveals something fundamental about the nature of space itself. Light is not crossing a fixed distance. It is running on a treadmill that stretches as it runs. When a photon leaves a distant galaxy, it begins its journey toward us at the fastest speed anything can travel, 300,000 kilometers per second. Nothing with mass can match it. But as that photon races through the void itself is changing. The space between that distant galaxy and our own is growing, expanding, stretching like fabric being pulled. The photon keeps moving at the speed of light. It never slows down. Yes, but the distance it needs to cross keeps increasing even as it travels. So a photon that left a galaxy 13 billion years ago has been running through space that continuously stretched beneath its feet. By the time it arrives, the galaxy it left has moved much farther away. The light traveled for 13 billion years, but the galaxy is now 46 billion light years distant. Some photons began their journey early enough, from close enough, that they could outpace the stretching and reach us. They arrived. They became the images in our telescopes. They told us their stories. Others, from farther away, are running on a treadmill that stretches faster than they can run. They will never arrive. Not in a billion years. Not in a trillion. Not ever. The distance grows faster than they can close it. This is not a violation of physics. Nothing is traveling through space faster than light. The speed limit remains absolute. Instead, new space is being created between objects. The galaxies are not fleeing from us. The universe is simply growing more road between us and them faster than light can cross it. Think of it this way. Two ships sit motionless in an ocean. Neither one is moving, but the ocean itself is expanding, adding more water between them with every passing moment. From each ship's perspective, the other appears to drift away. Neither ship is traveling. The distance simply grows. This is what the universe is doing. Every moment, at every scale, everywhere. And something is making it happen faster. Roughly 68% of everything that exists is not matter. And it is not energy in any form we can detect or measure directly. It is something else. Something that fills empty space and pushes it to expand. We call it dark energy because we do not know what it is. We only know what it does. It accelerates the expansion, year after year, eon after eon. The stretching of space is not constant. It is speeding up. The observable universe is an island, and the ocean is rising around it. The horizon is not static. It is shrinking. There are galaxies visible tonight that will not be visible in the distant future. Not because they will die, not because they will fade, because the space between us and them will grow so fast that their light will never bridge the gap again. They will cross the horizon. They will vanish from our sky. Here is a question that should keep you awake. Yet if the universe has been expanding for 13.8 billion years and the expansion is accelerating, What happens to everything we can currently see? What happens to the ancient light still traveling toward us? What happens to the story of our own origins? These are not abstract concerns. They have answers, real answers that cosmology can calculate with precision. The treadmill is speeding up. The photons are falling behind. The light we capture tonight carries information that future generations may never access. The galaxies we photograph now are witnesses to an era that will eventually become invisible, not lost to time in the ordinary sense, lost to distance in a way that no technology, no matter how advanced, could ever overcome. This is what dark energy does. It does not destroy the universe, and it does not end existence. It separates, it isolates, it stretches the fabric of reality until neighbors become strangers and strangers become nothing at all. The boundary of what we can know is real. It is precise, it can be measured, and it is closing in. Not quickly, by human standards. Billions of years will pass before the effects become dramatic, but the process has already begun. The acceleration started roughly 5 billion years ago. Every day, the observable universe contains slightly less of what exists beyond it. We live in a window, a narrow moment in cosmic history when the ancient light can still reach us, when the evidence of how everything began remains visible in the sky, when the story of our origins is still being delivered, photon by photon, from distances so vast they strain comprehension. Yes, that window will not remain open forever. The darkness between stars is not empty. It is expanding, growing, claiming more of the universe with every passing eon. And there is nothing that can stop it. The process is already underway. The separation has begun, and it will not stop. 100 billion years from now, give or take, every galaxy beyond our local cluster will have crossed a threshold. Not a physical barrier, not a wall you could touch or see. Something stranger, a boundary drawn by the expansion of space itself. The light from those galaxies will still be traveling. The photons will still be moving at the same speed they always moved. But the space between us and them will be stretching faster than light can cross it. They will fall behind. They will slip away. They will disappear. Not destroyed, not dimmed, simply unreachable. Imagine a classroom. A teacher stands at the front, writing equations on a board. History, physics, the fundamental truths about how everything began. A student sits at a desk, copying the notes, trying to understand. But before the student finishes writing, someone erases the board. Not quickly, slowly, letter by letter. The student looks up from their notebook, and the board is blank. The lesson was taught. The information existed, but by the time they needed it, it was gone. That is what the universe is doing to its own history. The cosmic microwave background, that faint glow, that echo of the first light that ever traveled freely through space. It has been stretching since it was released, red-shifting, cooling, growing fainter with every eon. In 100 billion years, and it will have stretched into wavelengths so impossibly long that no instrument could detect them. No antenna could pick them up. No sensor could register their presence. The echo will fall silent. The first voice of the universe will fade below any threshold of hearing. A civilization arising then would have nothing to listen to. They would look out at the sky with perfect instruments. They would measure with flawless precision. They would build telescopes more powerful than anything we have imagined. And they would see only their local group of galaxies, a handful of objects, a small cluster, neighbors in the dark, nothing else. No distant galaxies retreating at measurable speeds. No cosmic web threading through the void. No structure beyond their immediate surroundings. Just darkness. Just silence. Just the quiet company of the few objects close enough to have stayed. The early universe was not slow and gradual. It was a factory, urgently, violently building cosmic architecture while the window remained open. We have seen the evidence of that frantic construction, the impossible galaxies, the monsters at the dawn of time, The structure that should not yet exist, we have watched the factory's output with our own instruments, caught the light it sent across the ages. Future civilizations will inherit none of this. Their archaeologists will be working a dig site that has been paved over. The artifacts are not hidden beneath the soil, waiting to be discovered. They are not buried in some archive, waiting for the right key. They simply no longer exist within any boundary those scientists could ever reach. And the evidence has crossed the horizon. It has slipped beyond the edge of the knowable, and the edge keeps moving inward. Here is what haunts me about this. Those future scientists would have no way of knowing they were wrong. Their observations would be consistent. Their mathematics would balance. Every measurement they made would fit into a coherent picture. They would look at their small group of galaxies, see no expansion beyond it, detect no background radiation, find no distant structure, and they would conclude, reasonably, logically, that the universe has always been this way. A few galaxies, eternal, static, alone. They would construct a model. It would explain everything they could see. It would predict the behavior of everything they could measure, and it would be catastrophically, tragically incomplete. And not because they made a mistake, not because they lacked intelligence or dedication or curiosity, because the truth had been carried away before they were born. The universe would have erased its own story. This is not hidden knowledge. This is not a secret kept in some locked vault. This is knowledge that ceases to exist. The wavelengths stretched beyond detection. The photons red-shifted into invisibility. The galaxies carried past the horizon by the same expansion that created them. The information is not merely unknown, it becomes unknowable. Not concealed, but deleted. Sit with that for a moment. The silence of a sky with no distant light. The emptiness of a cosmos with no visible structure. The loneliness of a civilization that believes it is all there is, because everything else has been carried away. It's as they would look up and see only their neighbors, a few 100 billion stars in the combined mass of their local group. Magnificent, yes. Beautiful, certainly, but isolated. Cut off from the true scale of what exists. Cut off from the history of how it all began. Cut off from the evidence that once, in the distant past, the universe was young and hot and full of possibility. They would never know about the factory. They would never know about the frantic construction, the impossible speed, the monsters that formed in the first 500 million years. They would never know that there was ever anything to explain. The questions we ask today would not occur to them, because the phenomena that prompt those questions would be invisible. The cosmic web would be a concept that never forms in their minds, and the Big Bang would be a hypothesis with no supporting evidence. The expansion of space would be undetectable, because everything far enough away to show the expansion would have already disappeared. Their physics would work. Their equations would balance. Their predictions would match their observations. And all of it would describe a tiny, static, orphaned corner of something they could never see. This is not a failure of science. It is a limitation built into reality. The boundary is not imposed by our instruments or our mathematics. It is imposed by the structure of space-time itself. Light can only travel so fast. Space can expand without limit. Eventually, the race is lost. Eventually, the horizon wins. We happen to live in the narrow window when the evidence is still arriving, when the ancient light can still reach us, when the story of our origins is still being written in wavelengths we can detect. We are the civilization that gets to see the whole sky. We are the scientists whose dig site has not yet been paved, but the construction crews are already at work. The horizon is already closing. The evidence is already fading. Every day, photons that once could have reached us slip past the point of no return. Every century, galaxies that were visible to our ancestors move closer to the edge. The process is slow by human standards. It is relentless by cosmic ones. What we see now, no one will see again. What we learn now, no one will learn later. The classroom is still full of lessons. The board is still covered with equations. But the eraser is moving, slowly, steadily, across the surface, and eventually there will be nothing left to copy. The universe is not dying, it is not ending, it is simply forgetting. Forgetting itself, forgetting its origins, forgetting the fire and fury of its youth. And in 100 billion years, the forgetting will be complete. The sky will be quiet, the evidence will be gone, and whatever minds arise to wonder about their place in existence will wonder alone, in a darkness that reveals nothing of what came before. The darkness that awaits future civilizations is not our darkness. Not yet. We live in a different time, a privileged time, a window. Right now, tonight, as you listen to these words, ancient light is still arriving. Of photons that began their journey when the universe was young are completing that journey at this very moment. They are crossing the threshold of our atmosphere. They are striking mirrors and sensors. They are becoming data, becoming knowledge, becoming answers to questions we have asked for centuries. The cosmic microwave background is still detectable. The afterglow of creation, stretched and cooled across billions of years, still paints itself across our sky in patterns we can measure. The early galaxies, those impossible giants that formed too fast, are still visible to instruments sensitive enough to see them. The supermassive black holes at the dawn of time, the ones that should not exist, are still sending their signatures across the void. The evidence has not yet been erased. We are witnesses. That is the word that fits. Yet we are witnesses to a crime scene that is being cleaned even as we investigate. The detectives are still on site. The fingerprints are still visible. The footprints have not yet been washed away, but the cleaning crew is working. Slowly, steadily. Every moment, the scene becomes a little less complete. The universe did not wait for us. It did not pause its expansion while we developed radio telescopes. It did not slow its acceleration while we learned to grind mirrors. It did not hold its oldest light in place while we argued about funding and launch schedules. The universe simply continued, indifferent, patient in its own timeless way. And now we have instruments capable of seeing what remains. Instruments that exist in this narrow window between when the evidence was created and when it will disappear forever. And the James Webb Space Telescope is one such instrument. It hangs in the cold between worlds, gathering photons that have traveled across cosmic ages. It sees what no human eye could ever see. It records what would otherwise be lost, but it will not last forever. The telescope's mid-infrared instruments require temperatures so cold that ordinary materials would shatter. This cold is maintained by a supply of cryogenic coolant, a finite reservoir that cannot be replenished. Once launched, once positioned at its distant outpost, the telescope became an island. No service missions, no refueling, no repairs, just the slow expenditure of a resource that will eventually run dry. Approximately 20 years, that is the estimate for how long the coolant will last. 20 years of full capability, 20 years of seeing the universe in wavelengths that reveal its oldest secrets. After that, something gradual will begin. The telescope will not simply stop working one day. It will not go dark in an instant. Instead, it will lose capabilities slowly, layer by layer, like an eye developing cataracts. The mid-infrared vision will fade first as the instruments warm beyond their operating threshold. The telescope will become partially blind to the oldest light, even as it continues gathering signals from closer, newer sources. The near-infrared instruments do not require the same extreme cooling. They may continue operating long after their mid-infrared companions fall silent. The telescope will still see, but it will see less. The deepest red wavelengths, the most stretched and ancient photons, will slip beyond its perception. Yet this is not a failure of engineering. It is simply physics. Every instrument has limits. Every mission has an end, but other eyes are being built. Somewhere in the Chilean desert, construction proceeds on a telescope with a primary mirror 39 meters across. That is nearly 6 times wider than than the Webb telescope's mirror. When it opens its eye to the sky, it will gather light with a hunger that dwarfs anything we have ever built. Ground-based, massive, a giant watching the heavens from a mountaintop. Elsewhere, engineers are preparing a telescope named for Nancy Grace Roman, a woman who championed astronomy for decades. This telescope will carry a different gift. Its mirror will not be larger than Webb's, but its field of view will be 200 times wider. Where Webb focuses on small patches, is staring deeply at individual targets, Roman will survey vast regions. It will sweep across the sky, cataloguing billions of objects in systematic passes that map the universe at unprecedented scale. And another observatory, named for Vera Rubin, will join this effort. It will watch the same patches of sky night after night, year after year, detecting anything that changes, anything that moves, anything that flickers or fades or suddenly appears. It will see the universe not as a static portrait, but as a living thing, changing over time. These instruments represent something profound. They represent a choice, a collective decision that we will not simply accept the window we have been given. We will use it. We will peer through it with every tool we can devise. And we will gather what can be gathered before the cleaning crew finishes its work. The window of observation is not eternal. It is not even especially long on cosmic timescales. We are simply fortunate enough to exist during the brief moment when the universe's autobiography is still legible. Think of a library, an ancient library filled with scrolls that describe the birth of everything. The scrolls are written in fading ink. The pages are crumbling at the edges, and the library itself is sinking, slowly, into the earth. Each year, the basement floods a little higher. Each decade, another shelf becomes unreachable. We have found this library. We have learned to read its oldest texts. We are copying what we can, as fast as we can, while the floodwaters rise around our ankles. The universe did not wait for us to be ready, and it began its great erasing long before we existed. The expansion that now carries galaxies beyond our horizon started before Earth formed, before the Sun ignited, before the Milky Way completed its first spiral arm. We arrived late to the story. We developed eyes capable of seeing the evidence only recently, in cosmic terms. A few hundred years of telescopes, a few decades of space-based observatories, a handful of years with instruments sensitive enough to see the dawn. And now we look. We look with everything we have. We look because what we see now, no one will see again. We look because the photons arriving tonight are the last of their kind, the final messengers from an era that grows more distant with every passing moment. Each passing eon erases a little more, stretches a little more light beyond our reach. It carries a little more evidence across the horizon where it can never be retrieved. The crime scene is being cleaned. The witnesses are still present. The testimony is still being recorded. For now. But what does "for now" actually mean? What have we learned, really, from all of this? From the universe-breaker galaxies that shouldn't exist. From the black holes that grew too massive too quickly. From the cosmic web that wove itself together before the loom should have been ready. From the dead galaxies that lived and died in what should have been the universe's infancy. From the grand spiral structures spinning in an era of chaos. These are not separate mysteries. They are the same mystery, wearing different masks. Every anomaly points in the same direction. Every discovery carries the same message, as the entire timeline of cosmic structure formation must be compressed, squeezed together, made to fit into a window that our models said was far too small. Something happened in those early eras. Something accelerated the assembly of everything. Either gravity behaved differently when the universe was young and dense, or mechanisms we haven't identified yet pushed matter together faster than we thought possible. Or both. Probably both. The standard model is not wrong. This matters. It correctly predicted the cosmic microwave background, that ancient glow from when the universe first became transparent. It accurately described how galaxies cluster on the largest scales. It anticipated the accelerating expansion driven by the mysterious energy-filling empty space. The model works beautifully for the universe we could already see, yet it simply had no data from the universe we couldn't see. Until now. Consider a recipe, one that has been passed down through generations. You've made the dish 100 times. The proportions are perfect. The timing is precise. The chemistry is exactly right. Every single time, it turns out exactly as expected. Then one day, you walk into the kitchen, and the dish is already on the table, fully prepared, still warm. But you haven't even finished preheating the oven. The recipe isn't wrong. The steps are correct. The chemistry is sound. But somehow, impossibly, the meal exists before you've completed the process that was supposed to create it. That's what Webb found. A universe that was supposed to be preheating, still gathering ingredients, still measuring out the proportions that would eventually become galaxies and black holes and the vast cosmic web connecting everything to everything else. Instead, the meal was already served, steaming, ready, as if someone else had cooked it using methods the recipe never described. The standard model is a recipe for a universe that took its time. Webb showed us a universe that was in a hurry, and it didn't bother to tell us why. You have to appreciate the universe's sense of timing here. We spent centuries building a beautiful, elegant model of how everything began. Generation after generation of scientists refining the equations, testing the predictions, gathering evidence that confirmed the theory again and again. Just when we developed the technology to finally check our work at the very beginning of time, yet the cosmos looked back at us and said, "Close, but not quite. Nice try though." The universe wasn't being cruel. It was simply being honest, showing us what was actually there, instead of what we expected to find. And what was there was activity. Relentless, furious, impossibly efficient activity. The early cosmos was not dark and quiet and slowly assembling. It was a factory, a production line running at speeds that shouldn't have been achievable, building structures on timelines that our equations couldn't accommodate. The standard model imagined a gradual awakening, a slow dawn where simple things came first and complexity arrived much later. Stars before galaxies, small galaxies before large ones, chaos before order, time as the essential ingredient, giving the universe permission to become interesting. Her Webb found the opposite. Complexity from the start, order emerging from chaos almost immediately, time compressed into impossibly thin windows where everything seemed to happen at once. Perhaps this is the strangest implication of all. If the early universe operated by different rules, if it assembled itself with capabilities we haven't identified, then the cosmos we inhabit today might be the anomaly, not the norm. Think about that for a moment. The relatively calm, slowly evolving universe of the past 10 billion years. The universe where galaxies drift apart gently, where new stars form at a leisurely pace, where structures grow incrementally over eons. We assumed this was the natural state of things, the default mode of cosmic existence. But what if it isn't? What if the hyperactive dawn was normal? What if the frantic assembly, the impossible efficiency, the compressed timelines were how the cosmos actually operates when it's young and dense and full of whatever energy drove that era? The quiet modern universe might be the exception. A tired cosmos winding down, losing capabilities it once possessed, forgetting how to build things the way it used to. Like an athlete decades past their prime, still moving but no longer capable of the explosive performance that once seemed effortless. We live in the universe's twilight, its retirement years, its long exhale after the frantic work of its youth. The dawn was not the beginning of a gradual awakening. It was the peak, the explosion of productivity, the era when the cosmos could do things it can no longer do. By the time humans arrived, the factory had slowed. The production line was winding down. The universe had already built most of what it would ever build. in those first chaotic eons when time and energy and matter conspired to create at impossible speeds. We see the products of that era, the ancient galaxies, now quiet and old, the supermassive black holes still anchoring galactic cores but no longer growing with the same ferocious appetite, the cosmic web, still spanning the void but no longer weaving new connections with the same urgency. The universe we inhabit is the aftermath, the quiet that follows the storm. The settling of dust after construction ends. Our models described this settled state beautifully. They just didn't know about the construction that came before, the frantic building phase that created the foundations everything else would rest upon. Our web isn't showing us that our physics is wrong. It's showing us that our physics is incomplete. The equations work perfectly for a universe that has already slowed down. They simply don't account for a cosmos that once moved faster than we imagined possible. Somewhere in those first few 100 million years, something extraordinary happened. Something we haven't fully understood. Something that built the scaffolding for everything that would come after. The photons still arriving carry that story. Each one a messenger from an era we're only beginning to comprehend. An era when the universe operated by rules we haven't yet discovered. When time itself seemed to bend around the urgency of creation. The evidence surrounds us. The testimony is being recorded. The witnesses are still speaking. And somewhere, drifting through the permanent dark, a machine listens. It hangs suspended at a point where the gravity of Earth and Sun balance perfectly. No ground beneath it. No atmosphere around it. Just the void and the ancient light that fills it. This is where the story ends, not with answers, but with arrival. The telescope was built to look backward, to catch photons that began their journey when nothing we know existed yet, before our sun gathered itself from scattered dust, before the atoms in your bones had coalesced inside dying stars, before any of it. The light was already traveling. It passed through emptiness for eons. Crossed distances that have no meaning in human terms, watched galaxies form and fade in its peripheral vision. And finally, after all that time, it ended its journey by falling into a golden mirror the size of a tennis court. That light carried a message. Not instructions, not explanations, nothing so generous as a roadmap, just a simple statement, encoded in wavelengths stretched by the expansion of everything. A statement that took billions of years to deliver. The message was this: we have been building since the beginning. We did not need your permission. We did not consult your equations. We did not wait. And you are late. The scientific community feared what this telescope might find. They built it hoping for confirmation, hoping the universe would cooperate with their careful mathematics, hoping the light from the dawn would show exactly what their models predicted: a slow awakening, a gradual assembly, patience written into the fabric of existence itself. And instead, the data came back wrong. Too many galaxies, too massive, too early, too organized. Black holes that could not have grown so large. Structures that could not have woven themselves so quickly. A cosmos that had apparently read a different set of instructions than the ones humanity had written. The fear was not that the instruments had failed. The instruments were performing flawlessly. The fear was not that the data was corrupted. The data was pristine. The fear was that the data was right, that the universe really was larger than they allowed themselves to imagine, faster than their speed limits permitted, more creative than their models could accommodate, more urgent than anyone had dared to suspect. The discoveries were not errors to be corrected. They were revelations to be absorbed. Yet the cosmos had simply been doing things while nobody was watching, building empires in the dark, lighting fires that would burn for billions of years, assembling the scaffolding that everything else would rest upon. By the time anyone arrived to look, the work was finished. The construction crews had gone home. Only the products remained, silent and ancient, waiting to be noticed. The universe did not wait. That phrase has echoed through everything the telescope has shown us. It appears in the impossible galaxies, in the overgrown black holes, in the cosmic web that was already woven when it should have been loose threads drifting through chaos. The cosmos operated on its own schedule. It followed rules we had not discovered. It built with efficiency we cannot explain. And then it slowed down. It settled into the quiet rhythm we mistook for its natural state and let us believe we understood it. We arrived late to a party that ended long ago. The lights are still on. The decorations still hang from the rafters. But the guests have departed. The music has stopped. We wander through empty rooms, finding evidence of celebrations we never witnessed. The photons keep arriving, billions of years old, carrying their ancient testimony, each one a whisper from an era that operated by different principles, each one saying the same thing in a slightly different wavelength. You were not here when it mattered. You came after. You are witnesses to the aftermath, not participants in the event. The telescope floats in its permanent isolation. It will keep gathering light for years to come. Each observation, another page in a history book we are only beginning to read. The darkness between stars is not empty. It is full of messages we are finally learning to receive. And the messages all say the same thing. You are late.